All right, we're switching gears. We're still in this second level of the complexity bullseye, finite state machines, CFLs. And now we're going to talk about the equivalent machine version to context-free grammars. And they are non-deterministic pushdown machines. And I'm going to tell you just what they are. We're going to do examples. We're going to try to distinguish between what they can do and what deterministic pushdown machines can do. And we'll talk about the structure and the applications of all these things today. Okay, questions? Everybody all right? So again, you guys are going to be involved in about 1 minute. A pushdown machine is just like a finite state machine, except we put in an extra piece of power. We put in a stack. And the finite state machine, instead of just being able to move from state to state, can also, every time it sees a symbol, manipulate the stack in the way that you're used to. It can push a symbol on the stack and or pop a symbol off the stack. Right? So every single step it moves a state, and then it also manipulates the stack. Right? That's it. That's what it can do. So if you want to make a picture of such a thing, just a little abstract picture, and then you can put it on some textbook that you write, instead of that Leonardo da Vinci thing. The finite state machine would be here. Here's the input, where every cell holds another symbol, and this arrow represents that the finite state machine is always looking at some particular cell, and it always moves uniformly left to right, step by step. It doesn't have the power to go back and forth. I mentioned that a finite state machine that does have the power to go back and forth, that actually doesn't give you any more power. In this version, we're sticking with the unidirectional movement and uniform movement of the machine. But I should mention that if you do allow two-way movement on a pushdown machine with a stack, then you can do more things than you can without the two-way movement. So in this case, we have to be careful to just imagine that we're moving left to right, and we can't go back and look again. Okay, finite state machines, it doesn't help, but here it would help. Okay, now not only can this finite state machine look and read input, but it also manipulates a stack, which we'll keep here, and we'll make a little bit bigger, just to distinguish it from the input tape. And the stack has symbols in it, and that's the top. So it can pull things off and put things in. And that's what this machine looks like abstractly. When we're going to write a program to do machines like this, we are not going to write it the way that you see it in some books is they just actually list the transition function, and it's quite mathematical looking and not so intuitive. We're just going to expand on the notation we use for finite state machines and add in the stack manipulations in that notation. So it looks very much like what you've been doing up till now, except with extra things on the arrows. If you define it formally, it's the same 5-tuple that a finite state machine was, but there's an extra 2 things. So it ends up being a 7-tuple. The extra 2 things, or an extra 1 thing, I suppose. The extra 1 thing is the stack alphabet, because you need to decide what kind of symbols you're putting in the stack. And the transition function is no longer as simple as it was, just going from a state and a symbol to a state. Now it goes from a state and a symbol and the top of a stack and a stack symbol to a state and a stack symbol. So everything's a little more complicated formally, but intuitively it won't be so bad. So let's start with some specifics. Let's take a language that we know is not a finite state, that has no finite state machine, that's not regular, and let's try to build a pushdown machine for it. Let's first do it intuitively to make sure we know how we could use the stack to help us here, and then we'll actually write the machine out, so you'll see your first machine. So who's got an idea? How do you accept things like this? You only have a finite number of states, and depending on what state you're in, you're allowed to manipulate the stack depending on what symbol you see. So let's think of an idea before we write it out.
Every time you get a 0, you push something on the stack.
Okay, so read a 0. Read the thing left to right. If you see a 0, we'll push something on the stack. Say an X will be for a 0. All right, so we're putting X's on the stack. And then when we see a 1, we just start popping things off the stack. And if we hit the empty string, or when we hit the end of the string, the same time the stack is empty, then we know that it's OK. And if we hit anything else along the way, we just die.
So like if the stack runs out and you try to pop, that's just the end of
That's a crash, right. That's a non-accepting computation, right. Or if there's no arrow defined, if there's a symbol on the stack that doesn't say what to do with it. That's a crash. The same, pretty much the same as before. If there's an error that isn't defined, it's a crash, and it's non-acceptable. So let's write a machine that does it. Here's how we'll do it. We have a start state just as we did before. And we'll indicate semantics of these states. So this will be the push state. This is the state that we're hoping to see zeros. And we're going to push things on the stack when we do. All right, so let's write it out. If we see a 0, we stay in the state and we keep pushing. If we see a 0, we stay in the state. But there's more that needs to be on that arrow. We have to say what was on the stack before and what we want the stack to look like now. So this is a matter of notation, and this is my own notation, which is kind of the way a lot of books do it nowadays. It wasn't the way people did it 10 years ago, and I don't know if our book does it precisely the way I do it, but it's close enough. What I like to do is I like to write the top of what's on the stack currently as the next symbol. Right now, the stack we imagine would be empty, and I think of Z as the empty stack. You can check if the stack's empty. Z is the bottom symbol in the stack. So if the stack is empty, then we're going to put an X on it, and I write that like this, XZ. So this kind of notation is a push. I'm pushing something on the left of the empty stack. Okay? Yeah, Doug?
In the finite state machines, a lot of times we would have like 0, 1 to mean that it was an arrow for 0.
Oh, yes. Right.
Is it just contextual if you know that you're in pushdown machines, you know to interpret it this way?
No, I think that notation I use, 0, is really bad if I intend to do this later. I shouldn't do it. I shouldn't do it. I should use plus instead of comma, because I mean plus anyway. It's just that in mathematics, plus in this kind of theory area is always means union. And comma usually means union in math if you put curly brackets around it. So it's often used instead. But I should have been careful there and just wrote plus instead of comma, because these commas are different. These commas mean 3 separate things. 0 combined with the empty stack, push on the empty stack, and then go back to where you were. Yeah.
See what the 3 things are again?
Yeah, this is the symbol you're reading. Yeah. This is what the top of the stack looks like now. That's what the top of the stack looks like when you're done.
So
XZ.
Z is a stack?
Z is a symbol that sits on the bottom of the stack. It's the empty stack.
So what happens the second time through? So I've done that once. I have XZ. Now I get another 0.
You can't use this transition the second time through because there's an X on the top of the stack.
Okay.
Michael's right. I mean, if I just have this machine right now, it can't do any more pushing. It can only do 1 push. You're right. And I'd be dead, and I wouldn't accept anything. Well, I don't got any final states. I'm not accepting anything anyway yet. But you're right. That's a problem. We have to add in another transition. So I'll put it up here. 0ZXZ, 0 X. XX. So if you see an empty stack or you see an X, and there's a 0 as your symbol, push an X on the stack. This just means push an X on the stack if you see a 0. Sometimes, you see how I have 2 things here? Sometimes, if you just want it to mean this, you would write this. 0, anything, X, anything. Okay, whatever's on the stack, if you see a 0, stick an X on top of it. That's all this really means. I'm just being formal here, and I'm writing down all the possibilities. The only symbols in our stack are going to be X and Z, the empty stack. There's always Z. That's the empty.
The thing in the middle, is it just one? It's whatever's at the top of the stack? Do we look down multiple layers into the stack?
All you can see is the top.
The top.
Yes. It's a stack, right. It's a real stack. Like those plates in the cafeteria, I think. All right, so I'm reading the zeros. I'm reading the zeros. If I ever read a 1 here, what happens?
Pop a 0 off and go to a different state.
I need to go to a different state because I have to remember that now I'm in a popping mode. If I stay in the same state, I'd be able to push zeros on again, and I don't want to be able to do that. So if I see a 1, I pop. Sorry. If I see a 1, X, I pop. Here's how we write pop. We write the top of the stack like we do before, but here we say pop. OK? Sometimes books put an empty string there or something. But that confuses me because I always think of the empty string as being an input symbol, not... I just like to write pop. It's clear enough. And now we go to another state, which we'll call the pop state, because this is a state that we're doing popping from. And in this state, what should the transition be? We want to look for only 1s here. And 1X. we're going to pop. If you see a 1 and there's an x on the stack, pop that x off. You're matching up the 1s with the x's that represent the 0s that you pushed on before. Okay. All right, how do we finish this machine up? This machine doesn't have any accepting states. This machine doesn't do anything yet except push x's on a stack and then pop the x's off as it sees the 1s. What do you do next? Okay. We need another state. That'll be the accepting state. How do we get to that state? If you, well, because almost, that's the right idea. If we saw 1 and it's already an empty stack, what does that mean? That means we got too many 1s. So actually a 1z should go to a dead state. So it's going to be the empty string, z, and you're allowed to do this too. You're allowed to leave the stack alone. You're allowed to do nothing. You're allowed to push, pop, and no, don't touch it. See, actually, technically, you're not allowed to leave it alone. Technically, if you want to leave something alone, you have to push something on it and then pop it off. So you just go from one state to another. I mean, technically, all you can do is push and pop, but it doesn't affect your ability to leave it alone. You can just add 2 states. So we might as well say you can leave it alone. So you can leave it alone, and then you accept. So, yeah, questions?
Arbitrary question, but if the stack is empty,
Yeah.
then we can't pop anything off. And the way to find out what's on there is that how do we find out that it truly is empty? I mean,
Are you thinking of a particular string? And
I guess I'm remembering when we were doing beta sim.
Yeah.
We had to look at something. Oh no, that was only never mind. That was just to see the one below it. We had to pop it and look at. But we can see. What
yeah, you can just look at the stack, and if there's an empty symbol on top, it means there's nothing there.
Right.
Just no. That's okay.
Does this mean that these things basically have to be non-deterministic to be useful?
Oh, what a great question. That's an excellent question. A really excellent question. No, it's really a good question. And for finite state machines, whenever we had an e-move, that was automatically non-deterministic, right? Because it meant that you had a choice to follow the real symbol you just read wherever it tells you to go, or to follow that e-move somewhere else and follow the symbol wherever it goes. And that means you had a real choice. All right? Now, in these kind of pushdown machines, the presence of an e-move does not necessarily imply that it's non-deterministic. So what does it mean to be non-deterministic? Intuitively, non-determinism means that you don't know what to do, that you have a choice. And an e-move in a finite state machine means that you have a choice. But an e-move here doesn't necessarily indicate that there's a choice, because there's another piece of input that you have to combine with it before you can do anything. So on an e-move in a finite state machine, if I see nothing, I can always go down that arrow. But here, if I see nothing, I can't always go down this arrow. When can I go down this arrow? If I see nothing and the stack is empty. I'm not allowed to go down this arrow every single time. If I see a 1 and there's an x, I can do this pop. But if I see the empty string, I can't just do this pop because I feel like it, because there is no arrow empty x pop. If I put empty x pop on this loop, that would be a non-deterministic machine. Because then, seeing an x on the stack and not looking at any symbol, I could pop. Or seeing an x on the stack and seeing the 1, I could pop. It's 2 different choices. Yeah?
How are we constrained from, say we had 0, 3, 1 to the 7, and we come in and we pop our stack to empty, and then we just do an e-move over with the empty stack?
Chris asked another good question. And this really picks on a technicality. But before I answer it, let me make sure everybody understands this. The definition of non-determinism for these pushdown machines is long and complex, but intuitively it's very simple. If you don't have a choice in your machine at any step, then it's deterministic. E-moves do not necessarily give you choices because they're combined with stack symbols. So if you have a unique input stack symbol for every choice, it's still deterministic. Here we have empty z, so that's still going to be deterministic because there is no other z combined with anything off this circle. If Z combined with anything else off this circle, then it would be non-deterministic. Yeah, Don, I'll get to your question in a second.
You had said that if you had a 1 or empty X or a 1Z, I forget which one you used, that it would then be non-deterministic.
Yes, if I put this in here, empty X pop, that's non-deterministic because when I'm sitting here and I'm staring at the 1s, I can either read the 1 and pop, or I can just pop as many as I want without reading the 1.
Okay.
And that gives me 2 completely different computations for the exact same string.
I forgot how the empty worked for a second there. Okay.
Are implicit paths to dead states, those are okay in a deterministic pushdown? Like you don't have to draw everything.
Right. You assume that any arrows that aren't there are dead. Right. Right. But Chris asked a really, really good question, the answer to which requires a technicality that I really don't want to get into because it gets away from the gist of what's going on. But I do want to deal with the question because it's a good question. What if I throw in 0, 3, 1 to the 7th into this machine? What actually happens? We push through the zeros. We got 3 X's on the stack. We start reading the 1s. We start popping 1s. We pop off 3 1s. Now, if we do pop off another 1, we're going to crash. So that doesn't work. But after popping off 3 of them, we can read no symbol at all. Notice that the stack is empty. Go over here and accept.
But then you see another 1.
So,
You wouldn't be able to do it because you.
right. So at this point, then we still have more symbols on, and then we'd see a 1, and then it would crash. Okay. So it's right. It's similar to what you had before, but it's a little tricky because here you can kind of eat things up on the stack or decide when you're going to jump off. But it's still deterministic. Okay? There are some technicalities with this distinction between non-determinism and determinism that if it really bugs you, and I don't mind if you do this, if it really bugs you and you don't like this empty string and you just want to know when you get to the end of the string, use like a pound sign for, imagine there's a pound sign at the end of your input string. A special, terminating symbol, like a period at the end of a file or a control D or whatever there's at the end of a file. Imagine that comes at the end of your input and you're looking for it. And in that way, I could replace this epsilon with a pound sign and it would take away any of these funny issues. So that way, epsilon would be used for when you really want, kind of a random choice to go out, and pound sign would be used for when you hit the end. So if you want to do that and epsilon bugs you, then you can do that. But there's officially no problem with using epsilon here. It's okay.
So do we have to have some state going out of the accept state on 1s or 0s?
They're all dead.
Do you have
But
to draw it
keep
in?
this deterministic, don't we have to do that?
No, they're all there. I just didn't draw them. Every combination of 1 and 0 with X and Z is there, and they all go to dead states.
But if you don't draw it, that makes it non-deterministic, doesn't it? Because it doesn't have arrows going out on the... I guess...
Technically, right.
To be non-deterministic.
Right. In a deterministic machine, you assume the presence of every combination of input symbol. In this case, both the input tape and the stack tape. So just for convenience, because there's a lot of those, even for deterministic machines now, if we don't draw them in, we just assume that whatever ones I left out are there and go to a dead state. So I could draw them in if I want to. But it doesn't make it any less deterministic in practice. All right, everyone, questions about this example? This is the simplest example there is. This is the 0 to the n, 1 to the n, the one we couldn't do for finite state machines. And now that we added a stack, boom, we can do it.
You can put any symbol on the stack.
Yes. And in fact, the stack alphabet is as long as you want to make it. Just like you can use more than 0s and 1s. If for your input, you can have X's and Y's and Z's and as many as you want. And you're supposed to specify what the stack alphabet is before you start. I should mention, actually, that if I restrict the stack alphabet to a single symbol, like if I said you couldn't use anything but an X, then you can't actually get all the non-deterministic push-down machine power. It's not powerful enough. You have to allow a general stack alphabet. A stack with just one symbol is called a counter, because all it can do is count. Right? It can't do palindromes, for example, because it can't remember the pattern. It can only count. You need 2 counters to simulate a general stack. Yeah. So I could throw 2 single symbol stacks in here, and that would be the same as having 1 stack. So you need 4 counters to do a Turing machine. Maybe we'll do that if we have a lot of time next week. Yeah.
If the stack has a language that's equivalent to the language we're using in the machine, so for example, we're using ones and zeros, which means we've got two different symbols. The stack has two symbols. Does it have full power? I mean,
Yes.
If the language only has one symbol, the stack still only has one symbol, would it still have full power?
Oh, that's a good question. You mean if the input alphabet is just zeros, can you still do every context-free language over zeros with just a single stack symbol? I don't know the answer.
So it's
That's
not
a good question.
necessarily an equivalence with the language.
No, it's got nothing to do with that. You need general stack symbols to have full power in a non-deterministic machine. If you restrict it to one symbol, you don't have full power. But maybe for single alphabets, they're equivalent and it doesn't matter. I don't know. That's a good question. I'll think about it this afternoon. That's the kind of question I just put in a quiz and then it ends up being a paper 3 years later. Now, I don't know if that question is easy or hard, but it's interesting. I don't know the answer. Okay. Questions?
Do people build these machines?
You mean like in their backyard and stuff?
I mean, can you buy a pushdown machine with
A Radio Shack?
Yeah, with extra batteries. No, not really. I mean, you can simulate them. You simulate them. What Yak pretty much does is simulates the action of one of these pushdown machines, more or less. But you write a program to do this, and the program has the data structure of a stack. So you don't really, have a machine that just does this. It's too simple.
Well, there are like finite state machines you can buy, right? That do control stuff.
Oh, I see. You mean like...
That's one of those.
Oh, sure. There might be microprocessors that have programs that are really push-down machines inside them. But even you're not really buying finite state machines. You're buying a whole program that just happens to be simulating the finite state machine. Oh, I take that back. I bet you traffic lights are just finite state machines without... Nowadays, they're probably microprocessors. Yeah, you see, certainly 30 years ago, there were machines that were just finite state machines. And I'm not sure if there's actually, yeah. No, your toaster's a push-down machine. No. I didn't.
That's $3 for the setup.
$3 for the setup, yes.
Is there a historical, did somebody say, hey, look, I had found this finite state machine, and then somebody said, oh, if we add this, it becomes this?
You mean like what happens first?
Yeah, did it go that way, or is this something that was created later to build a hierarchy?
I don't know which formalization came first. I'm not sure. All the theorems about finite state machines were done, the basic ones were done in the 50s and then 60s. And context-free languages, same time, similar. And that's when compiler... Turing machines officially before that, right. Right. So I guess in some ways, here's a general mode of computation, and here's... and let's cut it down a little bit and get these other formalities. I don't know. Todd, do you know, from a linguistic point of view, which came first, context-free languages or finite state machines? No. Yeah. I'm not sure. I can look it up.
Numbers starting with Turing 0, 1, 2, 3. So
you might think they went in order, yeah.
The history of studying the brain is like that. You start with the brain and take a part of it out. See if it still works.
Yeah. That's like that pain in the ass kid on my block.
It might be the same. We're going to start with the complicated.
He's well behaved now.
Oh, okay.
All I can think of is Jack Nicholson. Okay, so that's a pushdown machine example. Non-determinism is a little bit different than it was before, but more or less the same idea. And what we're going to do is one more example. This time we have to think a little bit more. It won't be quite as easy as a 0 to the n, 1 to the n. And we'll need to use more than one symbol on the stack. And we'll do it together as a group. And we'll go around the room so everyone can participate. And there'll be a little trick involved. All right, so this and then there's ice cream at the end. This language is the language of even length palindromes. W can be any symbol over the alphabet 0, 1, and the R here means that you're reversing W. So it's any set of symbols over 0 and 1, followed by their reverse. That's what this notation
W is
means.
like a string, not a string.
W is any string. Here, W is an element of 0 plus 1 star. Okay, so W is any string in zeros and ones, and as long as you have its reverse, that will be in our language. So these are even length palindromes. Let's write a pushdown machine, and in fact, let's try, if at all possible, to keep our machines deterministic. Because, well, because we'd like to if we can. That's not very... Yes, an aesthetic principle. That's right. Okay. Well, it's going to be hard to keep it deterministic here. How come? How would you do this? What's an idea? Joe?
Read the first part of the string and then push on the stack and then pull them.
Okay. Read the first part of the string, and by that you mean the first half, presumably. So you read the first half, and you're reading zeros and ones. As you read the zeros and ones, we can put x's and y's. You can put zeros and ones on the stack too. Whatever. You put the zeros and ones on the stack. And now that you get to the second half, you're ready to see the reverse string. And since you put the first half on the stack, what you're going to see is actually hopefully sitting on the stack in the order that you're going to see the new symbols, because they're put on as a stack in reverse. So then, if they match, the new symbol on the top of the stack, we'll just pop it off and keep going. And as long as they keep matching, we're fine. And if the stack empties the second we get to the end of the string, then we say, OK. That's a good idea. But,
We don't know where to go.
right, how do you know where that middle part is? How do you know where the middle part is?
Can we do an arbitrary number of pushes and or pops for every input? Like you get a 1.
Officially not, but you can always do it anyway just by adding more states. Like say on this state I want to push 2 things on this symbol. So I go to another state, I push 1. That just goes to another state, pushes the other, and that goes back in the loop.
Okay.
So yes, you can do it, but it's not part of the official rules.
Okay.
We really do need extra states to simulate. Yeah, Joe?
Is there only one stack?
Yes, there's only one stack. Yeah. So here's what I'm going to do. Since nobody's screaming out the answer, I'm just going to make this over the alphabet 0, 1, and 2. And I'll put a 2 in the middle. So it's a different language. It's easier to recognize now. When you see the 2, then you send a message to Joe to start doing the second half. It's much easier, I know. But everything we do with this is going to be very similar to the way you do it without the 2. So we might as well do it with the 2 if it makes everybody feel better. And then we'll fix it. It is a good strategy to use in general. Mathematicians do this all the time. Computer scientists do this all the time. You have a really hard problem, and it just makes you uncomfortable, and you're not sure you can do it. But you see another problem that's really similar, and you're almost certain you can do it. So just do the one you can do, because very often your discomfort was completely a fantasy. And when you're done doing the problem that you thought was easy, you say, oh, that first one is really the same thing, and then you're done. Not very often, but it does happen. It does happen. It really does.
So can you just have one state that pushes whatever it is you get,
Yeah.
and then a second state that pops the same thing, and in the middle it's a non-deterministic. It always goes if the state's the same. That doesn't really describe something that looks like.
Yeah, no, actually, you're doing a great job. You have just the right idea, but you're doing it without the 2, and I want to do it with the 2. So I'm going to have the 2 that goes in between.
No.
And then we'll do what you're right, which is right. It's a good idea, Michael. Michael's smart. All right. We're going to do Joe's strategy here, so we'll call this state Joe. It's really the push state. All right, it's the Joe state. And we're going to just read zeros and ones. And as we read zeros and ones, we're going to push x's and y's. I don't want to push zeros and ones only because anybody who's not completely used to the notation yet is going to get mixed up which part of the comma is the symbol and which is the stack. And maybe none of you will, but I'll pretend I will. All right. I'm going to stay pushing here. If I see a 0, what do I do? I push in X. Do I care what's on the stack when I'm pushing? So I'm just going to write any. Okay, 0, anything, push an X. 1, anything, push a Y. Okay. I'm munching up the zeros and ones. If I see a 2, I shift over. Do I care what's on the stack if I see a 2? No. What if it's the empty stack? What if I see 2 right at the beginning? Still want to move over, right? Because it's okay just to see a single 2. So no matter what, any. What do I do with the stack here? Any. You leave it alone. Right. Officially, I should push something on it and then pop it off. I should have that extra state. But think of that as a shorthand for doing that double movement. So I leave it alone, and now I'm ready to go into the popping state, or we'll call it the matching state, because that's really what it is, matching or popping. And now as I read symbols, I will be matching them off in reverse order to the palindrome. So I'm hoping to find things like 0, 0x pop, and 1 y pop. If I hit a z when I'm looking at a 1 or a 0, I'm dead, right? That's no good. If I hit a 1x, I'm dead. If I hit a 0y, I'm dead. All of those arrows that I'm not drawing in here are implied to go to a dead state. You don't draw them all in on pushdown machines because there's just a lot of them. And it makes it ugly and messy. So let's assume that the ones that aren't there go to dead states. How do we finish this up and succeed? If you are at the end, you empty string, z, leave it. And that means everything matched. I'm done with my string. The stack is empty. I'm ready to move over and accept. If there happens to be more symbols here, I die. Okay? Let me stop for questions about this example. This is just one step more complicated than the one before, and not all that much more complicated. But it does show you how you get palindromes now. Questions? All right. So now let's do it this way, without the 2. Here's how we do it without the 2.
So you have to try every possible.
Let's think about what this means. This is really a non-deterministic machine. How come? It's because at this point, if you see a 1 or a 0, and something's on the stack, you don't know whether to do this arrow and push, or whether to ignore the 1 or 0, thinking of it as an epsilon, and switching over to this state. You have a real choice here. This represents the choice of every time you read a symbol, am I going to push it on the stack? Have I reached the halfway point? Or have I not reached it yet? You have to guess. Now, if there is a halfway point where things match up, then you can make the guess at this point and get to an accepting state. That's good. That means we definitely accept all the palindromes. We just substitute this movement where the 2 used to be. The issue that could go wrong here, the reason why, if you're getting a sense, well, how is that so easy? There is a subtlety that could make this not work, and that is it's possible that when you put this in, other things have a chance to get to the final state that didn't used to. Maybe non-palindromes can get there. Is there any way to get from here to here with a non-palindrome? Well, let's think about it. This state has pushed a bunch of symbols on the stack. Then let's say you decide to go over here, and you match, 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 match. The only way to get to that final state is if everything you pushed on the stack the first time matched with all the succeeding symbols that you decided to match them with, and there's nothing left as far as the symbols go. Because when you go here, there better not be any symbols left on the machine. So if you just think about what this machine does, it can't accept anything except palindromes, and it accepts all the palindromes, and it's just as easy to write it with the 2 in there without it, except that now we have non-determinism. So we have to cash in on our power here. We couldn't just make it deterministic, but conceptually it wasn't a big leap. Questions? Yeah, Chris. And then.
So to get all of the palindromes, not just the even length ones, we would just go E0 or 1 on that hop.
What do you think? Chris says, what if you wanted all the palindromes instead of just the even length ones? then here, instead of guessing you're at the halfway point, you would guess that you've hit the middle symbol, and that middle symbol could either be a 0 or a 1. So instead of having an E here, you wouldn't even have an E.
You would have want even.
Oh, you want even also. You don't just want odd. Oh, if you want even and odd, then you could have a 0 here, or a 1 here, or an E here. And still, you would get only even or odd palindromes. Yeah, absolutely. And that would be even more non-deterministic if you want to. More choices. 3 choices at this point. Because you don't know whether you got the even one or the odd one, and you have to guess. Thinking of non-determinism as guessing is a good thing to do if you can get in that mode.
Would that go to 3
Yep.
different two-state sections? Like, would there be 3 arrows out of it?
No, because I think after you make the guess, you want to do the same thing afterwards. So it would look like this. It would look like this. Well, I would just add it on the same arrow. 0, any, 1, any. You would just add it right
You
down.
morph them together like that.
Yes. They really mean different arrows, but it's just, yeah. Neil, you had a question? Who had a question?
Oh, yeah. Can you convert this into a determinate machine?
No. No. Non-deterministic pushdown machines cannot be converted, generally speaking, into deterministic machines. You can't do the same trick we did before. And the reason we can't do the same trick we did before is because before, this is a really, really important question. So I'm not just, maybe I should slow down with this answer. It's a really important answer. You know what? I'm going to hold off because I'll talk about it in a minute. It's very important. It's going to be the next thing we're going to talk about. The relationship between determinism and non-determinism. You really need non-determinism here. You can't do this with a deterministic pushdown machine. There's no way to do it. You can't make that guess and get it right. You have a question, Michael?
Can these machines do WW?
This means all the strings whose first halves are the same as their second halves. So they can't. They're too stupid.
If you had 2 stacks, you need 2 stacks.
2 stacks, you could certainly do this. Right. But you can't do it with 1 stack. If you try the same strategy and you push the first half on the stack, then you got it in the wrong order. Could you do this with a 2-way machine? A machine that can go back? Yes, you could, because it can read it backwards. Remember I told you that if you make these things 2 ways, you actually increase power? So that's an example of that.
It sort of gives you another stack.
Not exactly. No, not quite another stack.
String.
Because a two-way pushdown machine is not quite as powerful as a Turing machine.
Right.
But it's more, well. The interesting thing is a 2-way deterministic machine. Let me show you a picture. Non-deterministic pushdown machine. Deterministic pushdown machine. I just told you that making this 2 ways, sometimes gives you more things that you couldn't do before. So a 2-way non-deterministic pushdown machine, can do a lot. And a 2-way deterministic pushdown machine can do more than a deterministic pushdown machine. But here's what it looks like. A 2-way deterministic pushdown machine is bigger, but there are some things that are here. Looks like this. Let me see if I can make the picture right. This is 2-way deterministic machine. A 2-way deterministic machine has some things that can't be done with a non-deterministic 1-way machine. But there are some things that a non-deterministic 1-way machine, there are some things a 2-way machine can do that non-deterministic machines can't do, and things that non-deterministic machines with 1-way can do that 2-way deterministic machines can't do. It's not just this containment thing anymore. Suddenly it starts to spread out. Remember that picture Mike Zipser put up on the board with all those levels, and then they started to cross over each other, and he was at a different level. He was in the co-NP and RP and all these other classes. But people who do his kind of research, they live in that world of trying to figure out the relationship between the classes. And you see diagrams like this all the time. Yeah, Chris?
Does it actually encompass all of deterministic?
Oh, yeah, it does. I should write it like this. Yeah, it does. That's better. You're right, right. Anyway, that's a side thing.
You could make a machine with a cube rather than a stack. Is that a different kind of thing?
No, that's an exam question. What do you think? What do you think about a queue? How many stacks can a queue simulate? Can a queue simulate a stack at all? If you wanted to do pushing and popping like a stack, and all you had was a queue, how would you do it? Should I let you think about it for a while? It's a good question. This hierarchy, 0 stacks, 1 stack, 2 stacks. Is there any hierarchy with queues? Maybe when you throw one queue on, you're already up at the Turing machine stage. Maybe it's 1, 2, 3 queues. I mean, how do they relate? Are queues more powerful than stacks or less powerful? Things to think about. I'll let you think about that. We'll move on with some simpler stuff. It's a very good question.
Take it off the exam now.
I need, no, it's not on the exam. How come nobody's asking just like nice, straightforward questions? Jeez. All these really, excellent questions. Really excellent. You're thinking just like you should be. Okay. We just did even palindromes. Now we're going to do this. We're going to do the complement of even palindromes, things that are not even palindromes. Now, I need to remind you of something very important. Context-free languages are not closed under complement. Just because we had a way of getting even-length palindromes does not mean there is any way to get the complement. You can't just toggle the final and non-final states like we used to. And I want to think about that and go slow with that for a minute. Why can't you just toggle the non-final and final states for these non-deterministic pushdown machines? Why can't you just reverse everything? Wherever you used to end up and accept, now you reject. And wherever you used to end up and reject, now you accept. I'll give you a hint. If it was a deterministic machine, you could do that. Deterministic machines are closed under complement. Deterministic context-free languages are closed under complement. Let me tell you what that means. If you take the complement of a deterministic context-free language, you get another deterministic context-free language. It stays there. If you take the complement of a non-deterministic context-free language, you don't necessarily get one. It goes out possibly into a higher level. So you can do the final toggling trick for deterministic context-free language. It's the same trick we did for finite state machines, no more complicated. Why doesn't the trick work for non-determinism? Because it didn't work for non-determinism for finite state machines either. If you toggle states in a non-deterministic finite state machine, you don't get the complement language. You end up accepting all the places that you had a chance to reject before. And the states that you had a chance to reject are not the complement. The complement should be all the ones that always get rejected. Non-determinism doesn't complement easily. So you can't just do tricks with non-determinism by toggling states. So there's no obvious way to show that non-deterministic context-free languages would be closed, and in fact they're not. Nevertheless, in this case, we can still get the complement. Doesn't mean we're definitely stuck. Just means we're not automatically in the ballpark. Before I go on and work on this, context-free languages are closed under what operation? Not complement, but under what easy operation? Under union. Because if you have a context-free language, you can do it as a grammar and take your start symbol and point it to the two start symbols of your grammar, and that's the union of the two. You can do the same thing with machines by doing the epsilon trick at the beginning. Just here's the two machines. You had another machine with a new start state. Epsilon, ZZ, go to each of the machines.
That's deterministic even with those epsilons?
No. Deterministic machines are not closed under union.
It doesn't say you.
When you say CFL,
Context-free languages are, CFLs are the same as non-deterministic pushdown machines.
Right.
This means non-deterministic, this means deterministic. These are closed under union, these are closed under complement. These are not closed under union just because of what Chris said, because the way you would normally do it is by making these E moves, and that's non-deterministic. You have a choice this way or that way. There's no way to get a general union of two deterministic context-free languages together. And in fact, here's a classic language that you can prove requires a non-deterministic pushdown machine. It's this deterministic one unioned with this deterministic one. These two together require a non-deterministic machine. There's no way to do it with a deterministic machine. And that's a counterexample to the hypothesis that they might be closed under union. They're not. Everyone knows how to do this with a deterministic machine? Anybody know how to do this with a deterministic machine? You push the zeros on, and then when you read the ones, instead of popping every time you read a 1, the first one you read, you just move to another state that says I saw 1. And the next one you read, you pop. Then you go back. So you have a little double loop reading pairs of 1s before you pop. It's not too bad.
Twice.
You can, but then,
You
well,
can push it twice.
you could push it twice and then just pop once on the other side. Is that what you mean? You want twice as many 1s as zeros. So either you're going to read 2 1s to match each thing on the stack, or you're going to push twice as many on the way in and then just pop one at a time. I don't want to get into the details of that. That is a homework question. But to do both of these requires non-determinism. You can't mix them together deterministically. So keep that in mind. Neither one of these is closed under intersection, because intersection would require 2 out of the 3 operations of union, complement, and intersection. 2 out of the 3. You'd require, if you were closed under complement and union, then you'd be closed under intersection. And neither one of these is closed under both complement and union.
Why don't we have the TAs make a little table for us?
I can pass out a table for you.
I actually, from when I took this before,
You have a big table?
it's the entire class on a sheet of paper.
Ooh, we'd like that.
Yeah, you won't want to see it to the end. You'll understand.
Okay, I can make I can Xerox a copy of all these closure properties and what's there and what's not. This is actually kind of a slick trick to know this, though, because there is a trick when we talk about undecidability later, where you go ahead and you take 2 context-free languages and you union them, and then that's definitely context-free. And then you take their complement, which ends up turning into deterministic context-free languages, and well, I'm really off. I'll do it later. I want to get back to my mainstream here. I went off on a tangent and a double tangent. Let's get back to the mainstream. The complement of even-length palindromes. I want to hear some ideas. How can we make a plan for a pushdown machine that's going to get this? Everything that's not of this form.
We can start by intersecting something with odd length strings, because we know that it...
You mean odd length strings are definitely in this complement.
Right.
All right, so let's start there. So the first thing Doug mentions is that these are even length palindromes. We want the complement of that. So anything that's odd length is in the complement. Okay? How do you do something to accept odd length things? Anything odd, even, anything except. Make a finite state machine. Right? And we'll divide all the things in this complement into the odd length strings and the even length strings. The odd length strings I'll accept. E, Z, Z. If it's odd length, I'll go this way. And if it's even length, I'll go here. Okay, so I agree that Doug's right. We can divide this up into the ones that are odd length and the ones that aren't odd length. The ones that are odd length we definitely want to accept, and we'll do that with a finite state machine. You'll notice that a finite state machine is really also a pushdown machine. It just doesn't touch its stack. Just leave the stack alone the whole time. I wrote any here, so it's any. Just don't touch the stack. Leave it alone. And accept all the things that end up in the odd state. Or if it's not odd, if we don't make this non-deterministic choice and know that it's odd, if it's even, if we go this way, then what do we have to make sure?
Is that the same machine, except when you get to a point where the stack doesn't match, you go to a state where you always, an accept state you always stay in that has all the arrows?
That's one way to do it. Let's try to do it that way. So Michael's idea is to work on what he already knows from the last machine. And the last machine we were working with matches, right? And hoping that we guess the right halfway point. we'll do the same thing, but this time we'll look for a mismatch. And if we ever get a mismatch, we just die and go to a dead state.
No, if we get a mismatch, we
Sorry, if we get a I said it wrong.
go to win.
If we get a mismatch, we go to, we accept. Okay? So let's look for mismatches. And if, yes?
The matching, is that something you just get for free, or is that something that was implemented in a way that I missed?
You mean checking that the symbols in the second half match the symbols in the first half? We got that because when we read the symbols in the first half, we threw representations of them on the stack. And then when we read the symbols in the second half, we matched the symbols we were reading in the second half with the symbols that were on the stack.
So the comparison is what the state is. I mean,
The comparison is comparing the symbol on the input to the symbol on the stack.
okay.
You'll see it again right here. We'll do it again right now. Yeah.
I missed something. Why can't we just toggle the states of the other machines?
Because the other machine is non-deterministic.
Oh, okay, this one's not going to be.
No, it's going to be non-deterministic too, but it's going to be a different non-deterministic machine. If you toggle the states of a non-deterministic machine, you don't get its complement.
Oh, okay, okay.
You get something else, and so it doesn't work. If it was,
It's not going to work the same way. You can't just do the thing.
it'll be a little right.
Because we can.
Let's see what happens. Let's start up. We're trying to accept things now that are even length, but do not have their first halves matching their reverse in the second half. How do we begin?
0 push X, DC 1 push Y.
So we're just going to push like we did before. So 0, any, push an X, 1, any, push a Y. That's just what we did before. And at some point we're going to guess that we're at the halfway point. Is that right? Seems okay? There's another way to do this, by the way. This is okay, though.
But if we jump early, we're gonna, or jump late, we're gonna be able to. We will find a mismatch. So we'll have to. Well, I guess we can do something with matching the.
If you find a mismatch and you didn't guess the right point, then we won't accept. We'll only accept mismatches that are comparing the right symbols. And we can do that by hopefully counting whether the stack empties out as we hit the end. So we can do the same test to make sure we get the right mismatch. So we are going to push everything on like we did before, guess one to go over here. And here, before we were looking for matches, now we're going to hope to get a mismatch. That's what's going to make us accept. We're hoping to get a mismatch. So
if we get a match, we
getting a
stay there. If we get a
mismatch-
mismatch, we go to an accept.
We still don't go to an accept state. We have to go to a state that then is going to empty out the stack.
right.
Yeah.
If we get a mismatch, we have to check that the mismatch occurred at a point where the number of symbols that we added onto here is going to equal the number of symbols that got popped off total. In other words, that this choice was made at the halfway point. You can make guesses in pushdown machines, but you often have to check those guesses were right later on. Otherwise, you allow acceptance with wrong guesses. The guesses are fine. It gives you power, but you have to check that the guess you made works out. Well, let's see how this works. If we get a mismatch, that means a 0, Y, pop, or a 1, X, pop. Anything else we don't accept. Anything else just gets killed, right? Or does
we
it?
need to loop around and pop.
If you get matches, does that mean you're dead? No, right? Matches are okay. You can get lots of matches as long as you get one mismatch. So we have to allow for these matches. 0x pop, right? 0, whoops, 1 y pop. Matches are okay. Match all you want. At some point, there's got to be a mismatch to get you to a final state. When you find that mismatch, out you go. Now we still don't accept yet, because this mismatch could have occurred at the second symbol and the fifth symbol, and the string is 200 symbols long. It meant that you picked the wrong halfway spot. So here we're now going to check that this halfway spot is a legitimate halfway spot, and we do that by continuing to pop symbols off, hoping that we get to the end of our string at the exact same time that the stack is empty. If that's the case, then we pushed exactly half as many before we made this move as we popped. So, say that again, Sham. Any, pop. And what's good? If we hit the end of the string, Z, Z.
And do we need the even odd thing on the top? Or would this
Yes.
We do need it,
match that also?
because this has no way of getting to an accept state on an odd length string.
'Cause we'll either-
The only way this can get to an accept state, and it's very important that the only way you can get there, is if you get a mismatch in an even length string. In fact, you can never ever get here on an odd length string. You only get there if there's no symbols left and the stuff you pushed was the same as the stuff you popped. And that means it has to be even length. Right? You want to try to fix it a little bit here to try to include this. It's not so easy. And if you could, it would make the machine, well, it might make the machine deterministic, which I'm pretty sure you can't do. So I'm not sure you can do any better than this. I'm not sure you could ever put these together in one. You might be able to, but the non-determinism would be hidden somewhere in here then. And this is easier to understand anyway, I guess.
What
Yeah.
if you had a different string, though? This is definitely even the way you have it set up, isn't it? W, WR. But if you had like W with 1 or 0, you know, with the odd, if you included odd length palindromes like we did last time, where you had even
Okay,
or
so
1 or
any
0,
palindromes, and then I wanted the complement of that,
Yeah.
then I just wouldn't have this part.
And then you put E.
And I
or
need to
1.
have something a little different there. Yes. Good. That's good. Good thinking. Yeah. This is not the only way to do this problem. I want to do it a different way because doing it a different way will give you a sense of kind of expanding your repertoire of how to do these things. And it will also help you do a very, very hard problem whose solution I will sketch for you today, but whose machine I want you to actually do for homework. So I'll tell you how to do it, but you're going to have to take the idea and turn it into a machine. And it's based on another solution to this problem, which I think uses a slightly more efficient use of the non-determinism. So let's do it. Different solution for this. The odd length is going to stay the same. That's just the way it was. Different way of doing this bottom half. Different idea. If we want something that's even length but isn't a palindrome, here's a halfway point. All we got to do to determine that is find a symbol here and a symbol here that mismatch, that are not the same. And the number of symbols from the left end here is the same as the number of symbols from the right end there. That's what a non-even length palindrome means. An even length non-palindrome. Everyone agree? Two symbols, this one the same from the left end, this one the same number from the right end, they mismatch. We did it this way by doing a lot of work. We actually, pushed on the first half, looked for the mismatch, checked for the halfway point. It's okay, but there's a nice, easier way to do it. Here's what we're going to do. We're going to read these symbols, pushing them on the stack as we go. And at some point, we are non-deterministically going to guess that this is the symbol right here that's going to be the mismatch. And we're going to remember it. And then we're just going to move across the tape, ignoring everything we see, until we non-deterministically guess that we're going to match it with this other symbol. If they mismatch, we're okay. How do we check that we made the right guess? Before we guess this, we push symbols on. We did that for a reason, because we counted how many steps it took to reach this cell. When we guess again later, we will then pop those symbols off as we read the symbols to the end to make sure that the number of slots between the left end and this guy is the same as the number of slots between the right end and this guy. And we'll consider this a legitimate match or mismatch only when the pushing here matches the popping there. That avoids a lot of these inner loops that we were doing before. Right? If you don't get the idea yet, follow along as we build the machine. And then you'll see the machine right in front of you, and we can go through it in an example. Here's what we're going to do. We're going to read symbols 0s and 1s and push them on the stack as we go. But we're not going to push the symbols themselves on the stack. We're just going to count. We're just going to count 3 or 4 symbols, as many as it takes. So here's what it looks like. 0, any, x any, 1, any, x any. This is different than before. We are not remembering the symbols. We're just counting how many steps it takes until we decide we're going to look at this symbol. Everybody get it? Not yet. Some people get it. Not everybody's there. Reading symbols, counting how many we've seen. At some point, we're going to non-deterministically go, stop reading symbols, look at this symbol, and remember what it is. 0 or 1 on anything. Leave the stack alone. Don't touch it. I saw a 0. I saw a 1. Just like a finite state machine. We're remembering whether we saw a 0 in that arrowed box or whether we saw a 1. If we saw a 0, we're hoping to get a 1 later. If we saw a 1, we're hoping to get a 0 later. So this machine is going to work in parallel. We've remembered the state. We have something interesting about it. Okay, so if I saw a 0, now I continue to move along the string, completely ignoring what I see, not touching the stack, not doing anything, just marching along until some point I say, oh, I'm going to see another symbol, I'm going to see another symbol, oh-dee-do-dee-do-dee-do, I'm going to see another symbol. Now I want a mismatch. I decided here's a 1, I think this is the mismatching 1. And then afterwards I'll check whether the number of symbols I counted here is the same as the number of symbols that are left. And if they are, that means I'm ready to accept. So, in this stage here, we look at zeros, and we ignore them. We look at 1s, and we ignore them. And at some point, we decide, okie dokie, I see a 1, and that's a mismatch. 1, any. And I'll call that mismatch. Here, it's the same thing. 0, any. 1, any. 0, mismatch. So from this top way, if I get a 1, I get a mismatch. From the bottom way, if I get a 0, I get a mismatch. And that mismatch can be guessed at any point. This is a very non-deterministic state, because we can move along, or we can decide to go here. Yeah, Blake?
Is there some reason that you're restricting your stack alphabet to just being a counter? Because couldn't you just push, if you see a 0, push the 0 on the stack, or if you see a 1, push the 1 on the stack, and then match it up that way? And then later on, choose if the input's a 1, top of the stack is a 0, then the top, or the other way around?
I could do that, but I don't need to do that. That's more or less what we did last time, for the most part. If you did that, you wouldn't be able to just skip symbols here.
It seems like it would just make the two middle states, the I saw a 0
Here?
state and the I saw a 1 state, the same state.
Mm-hmm.
The I saw a 0 would just be if the 0 is on top of the stack. And the I saw a 1 state is if the 1's on top of the stack.
Oh, I see. I understand what you want to say. You want to read these things through and leave it. Yeah, you could do that. You could use the stack to hold it rather than the state to hold it. I understand what you mean. Sure, you could definitely do that. I just didn't think of that, but I did it this way. Yeah, you could definitely do that. Yeah, good idea.
You just want to have
The lower branch to I saw a 1, that's supposed to be a 1.
Thank you, Andrew. Yeah. Definitely. All right, so here we are. Now we made a guess, we get a mismatch. How do we check whether we're OK and we mismatch on the right symbols? At this point, 0, any pop, 1, any pop. And if we hit the end, when the empty stack shows up, then we accept. This is the check that the two symbols we guessed here, and we guessed here, that those two guesses are the right relationship to one another. This is really a different idea than the first way we did it. The first way we did it was a variation on the regular WW reverse, and this way makes use out of non-determinism in a way that encourages you to think of it as a higher level of guessing. You can guess things if you can kind of deterministically check that your guess was right. And that should remind you very much of that NP complete stuff we did, right? How long does it take? You make your guess for free, but then you have to deterministically check your guess. That's really what's going on here too. Okay, questions about this? We're going to do a really, really hard problem now, and I won't write the machine for it, but I will sketch out the idea. It's a puzzle kind of a problem that I could give you and you could think about for a week and not get. Sometimes you might get it in an hour, but it's a hard problem, and I would never give it just straight on a homework all on its own. I think it's too tricky. But if I give you the idea, then you should be able to write the machine. And it's not just a puzzle out of nowhere. It's kind of a nice problem. Michael asked me before whether we could do WW, and what was the answer? Can you do it with the non-deterministic pushdown machine? I said you couldn't. I haven't proved it. We're going to prove it next class with pumping lemmas and stuff.
Do it with a Q.
You could do it with a Q, I guess, huh?
Mm-hmm.
Yeah, so what does that tell you?
Yeah, but then you couldn't do the...
Oh, no?
Well, maybe.
You sure? You can do a lot with a Q, right? I mean, here's a Q. Q's first in, first out. And I want to actually do a stack, but all I got is a stupid Q, right? So every time I want to pop something off, it's not in the front, right? It's down in the back. So all I got to do is put something, I put my little marker in the back of the Q, and I pop things off the Q. Out, 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 out. Oh, there's my marker.
I just threw away the one I wanted.
No, but I can save the one before. I can actually loop it around, because I don't really want to lose them, right? Out they go and in back they go. Out they go, in the back they go. There's my marker. Come on, marker. Right in my pocket like a magician. And there's the one I wanted, the one that came out right before the marker. So I can do pushes and pops in a stack way on a queue. It just takes a lot of work. It's a big simulation. A single push and pop is a linear operation that takes time proportional to the number of things in your queue. But you can do it. You just pay for it. Blake, you had a question?
No, I was just going to say that, but you need the additional,
Yeah.
additional state that will build the thing you popped off.
Right, but that's one state, that's okay. And you also need extra time. So anyway, a queue can do one stack. Can it do two stacks? Well, you think about that. Can it do two stacks? Maybe.
You put an intermediary symbol.
Yeah.
You can interleave the stacks. It can definitely do two stacks. Queues are very powerful. More powerful than you think. Especially how much attention stacks get.
Is it Q that you can pop off the...
I don't get it. It's not important.
Burning the candle on both ends? You have a question?
Well, I
It's okay.
figured out how a Q can simulate a stack yet.
Oh, it is important that you get it, but you don't have to get it right now.
Right.
And you will get it probably by lunch.
So many things.
As with so many things. All right, let's work on this. You can't do this with a non-deterministic pushdown machine, and we could work all day long and not be able to get it, and we will never get it. But what's really cool is that you can get its complement. And the reason I did the second way here is because how do we do the complement of WW reverse? The first way, we massaged the way that we did WW reverse, right? We did its complement by fiddling with the way we did the first one. Well, that's not going to be a good strategy here because we don't have any way to do WW. So we're completely on our own. And we need an idea that's completely unique. That's why we did this one in a different way. Because at least this idea can build on that idea. Everybody okay so far? Getting tired. You're tired. All right, let's think about this. We're going to think about it like a puzzle, not with any detailed machine written down. We're just going to write a picture on the board and think for a minute. If we mimic the idea here, what we'd like to do is make that same kind of a guess here and a guess here. But what's the condition that we want to check here? We want to check that the distance from the left end here, this distance, is the same as the distance from the middle to this one. So let me now suggest a bunch of bad ways to do this. We'll push symbols on the stack like we did before, remembering how many symbols it took to get here. And then we'll just randomly move along until we get to this guy and guess where the middle is. And then we'll start popping symbols and guess this one. And now all we have to do is check that we guess the right spot for the middle. But the way we guessed the right stop for the middle before was that we used our stack to remember all the symbols until we got to the middle. And I already used the stack for this thing. Well, I could use another stack and keep one stack to store this stuff and one stack to store my guess up until the middle, but that's 2 stacks. So this way really doesn't work. And it doesn't work in such a fundamental way that when you're working on this puzzle and you're first learning about theory, your gut instinct is that there's just no way to do this because it just really feels like you're stuck. It feels like there's no way you can even squeeze out anything to help you. Anything you do seems to need 2 stacks. Doesn't it seem that way? I mean, how are you going to show that anything from here to here is the same as something from the middle to here without 2 guesses and 2 checks on those guesses? It's really tricky. It's really a neat solution. It's really hard to think of. What we want to do is make these 2 kind of checks that we're doing, checking that this is equal to this and checking that this is equal to this. The reason it seems hard is because we have 2 equal numbers that we're trying to check that they're equal. The half to the second half and this first part to this first part. And we can't do that with 1 stack. You count one thing, you can check one thing, but you can't count 2 different things unless you're finished counting one when you're ready to start counting the other. But these are not nested, right? So that won't work. I mean, you can count one thing and then count something else, but that's not what's happening here. So can we make these 2 counting things that we have to check down to 1? That's the trick.
Can we interleave our counting, like every other thing that we push on the stack? One, use a counting alphabet to count one of them, and a separate counting alphabet to count the other one, and interleave the symbols? So
I don't think so, because then when you're popping them off, what if you see something that doesn't apply to your count? You take it off, and then you find the one that does apply to your count. You take that off. Then you got to put that other one back on, right? How do you get it back on? I guess you could remember that you saw it. Where are you going to remember it?
Yeah.
You can remember it in the finite state. But you're limited in those finite states to a finite number. If you had another stack to put it in, you could do that. But that's where you get stuck. Good idea, but you get stuck. Joe, do you have an idea?
Could you put more than one thing on a stack? Well, in a stack space?
Sure.
So then you could just put your first string in the first item of the stack space.
Oh, I see. More than one thing in a particular symbol. No, every stack thing has one symbol.
Okay.
Right. And even if you could do any finite number in one space, but you can't make a general thing go in one space. That's not allowed. All right. Here's the best way for me to motivate this. Where's my big eraser? About halfway. Oh, a little less. Check this out. That's good, right? Here's the first symbol in the string. This is meant to be halfway. This is the first symbol in the second half of the string. Everyone agree? If I move over one, then here's the second symbol in the first half. Here's the second symbol in the second half. What's true about these 2 symbols that I want to find the mismatch in?
They're separated by half the total length.
Right. They're separated by half the total length. Now, as simple as that is to see when I stick an eraser up on the board, or maybe not so simple, I didn't notice this for a few hours when I did this problem. That's the only thing you really have to check, is that these 2 things are separated by half the length of the total string. Now that's something that only requires a single counting. All you really want to do is make sure that the amount of distance here equals the amount of distance here plus here. Let's see if we can figure out a way to do that trick. Figure out a way to check that the amount of distance in between these 2 symbols has to be the same as the amount of distance between here and here. Now that Don has noticed this halfway idea, we can focus on that. I'll redraw the picture, and we'll think about it for a minute.
arbitrarily large at the beginning, so we can do negative.
Or just non-negatives.
I'll make that color. We want the pink part to be equal to the blue part. And the part that we want to test on is this yellow part. Okay? And we want a unique time in the machine at which point we're going to guess this to look at this symbol, and at which point we're going to guess to mismatch at this symbol, just like we had in that machine. So these are going to be the guesses. And we want to make sure when we're all done that the number of symbols read in this pink area is equal to the number read in the blue area. So Chris had some idea that what should we do in the blue area when we look at symbols? We want to do what? Push or pop?
We should well, it doesn't really matter. We need to build our stack up with junk.
Junk, okay.
For a while, then stick a marker on it and start either counting up or down, and then change direction in the pink part, and then change direction again in the blue part.
Change direction, you mean if you were pushing, you pop, and if you pop, you push? All right, so let me give a little bit of a cleaner way of doing that idea. That is the right idea. In this area, until we get to this spot, we're going to non-deterministically sit and push X's on a stack while we read symbols. And at some point, guess to look at this symbol, just like we do there. So I'll say push X's. Then we look at this symbol. And after this symbol, we're going to start looking at symbols, non-deterministically deciding when to mismatch. And if we're not going to mismatch and look at the symbol, what are we going to do as we move here? We're going to pop these symbols.
And then if we empty, we start.
So this area will be called pop X's. Now the popping of the X's may or may not go all the way through the pink section. It probably won't. The halfway point here is around this spot. Okay, and the popping of the X's, the popping of the X's may or may not finish before or after the halfway spot. It will finish right after this pink spot. So the red spot's the, did I get it right? Not quite. Almost right. Push X's, pop X's. When this stack is empty, you start to push again. Call this section here push. And this is another random collection of symbols. It can be different from this. This might be 3 symbols and pop 3 symbols. This might be push 4 symbols. Okay, but I'll call it Y's just to show you that it's different from these X's. Then you make a guess, and then this section is pop the Y's. We're hoping that this pops off the second we get to the end of the string. Let's say that happens. Let's say you push a bunch of symbols, pop a bunch of symbols, push a bunch of symbols, and pop a bunch of symbols, and you hit the end of the string the second you pop this last thing off and the stack's empty. What do you know? You know that 2x plus 2y plus 2, 2x plus 2y plus 1, 2, equals the whole string. Everyone agree? Yeah, Donna.
When you actually put your marker, do you do a pop with that?
These things we won't do any pops or pushes. Okay. So we read 2x symbols, 2y symbols, and then these 2 symbols we read and didn't do anything with the stack. Here's the length of our string. The middle point is somewhere here. Not necessarily in the center of this pink area, but somewhere left and right in there. We don't know exactly where it is. We're never going to find the halfway mark. We don't care about it. We only care that the distance between these 2 symbols is exactly equal to half the string, or equal to the blue section. Well, what is the pink section? It's x plus y. The whole thing is x plus y plus the 2 symbols. So if this pink part is x plus y, then the blue part's also x plus y. This is really tricky, and it's very subtle. But here it is again. Push a bunch of symbols arbitrarily. Guess that you're choosing to look at a symbol. Pop those symbols off the stack. Now the stack's empty. Start pushing symbols again non-deterministically, guessing when to make a mismatch. Find a mismatch. At that point, pop the symbols that you have off the stack as you read the rest of your string. If your string empties out when your stack is empty, then you know that the middle part here, consisting of the popping of the first set and the pushing of the second set, was the same as the pushing of the first set and the popping of the second set. That they equal, not only are they the same, but they equal the length of the string. That means the middle section is half the length. That means they are separated by the right amount. The trick in this problem is not to focus on counting two things, but to focus on counting one thing. What we're really counting here is half the length of the string and making sure that these two things are separated by it. I want to give you this as an example, not to say, oh, look how hard these things can be, but more, here's a complicated idea. Show me how to do it with the machine. Even if you don't get this idea in detail, exactly why it works, you should be able to still simulate the pushes and the pops and the guessing by using this as a model and just mimicking this model and fiddling with it. And then if you don't get that, then ask me and I'll help you figure out how to do this. But this is one of the questions on your assignment 3 that you'll get next week. Yeah, question?
I mean, obviously in a linear sense, this is up, down, up, down. It's not that big of a deal, but translating it into one of these, I don't really understand what you did with this previous machine well enough to translate that. I might be able to do it, but it's a little bit confusing to me. I guess some of the transitions you're making. I guess how you know when you're doing what. I mean, I realize that when you make one of these machines, you're defining a language, and so you don't have to know when you're doing what. But you didn't. I just sort of felt like.
Well, you do have to know when you're doing what. It's just that it's non-deterministic. So if there's a lot of things this machine could do, and only one of them is going to get the right answer,
right.
presumably.
And if you do the wrong thing, it's not in the language. But
no, if you do the wrong thing, it still may be in the language. You have to keep trying to try to do the right thing. If you can find one way to get to a final state, then that string's in the language. You can find 20,000 ways not to get there, and that doesn't mean it's not in the language. The only time it's not in the language is when all the ways you try don't get to a final state. Then it's not in the language. In non-determinism, something's not in the language if every single path that you try doesn't get you to a final state.
Sure.
These are brute force solutions.
Yeah. Yeah.
But
yeah.
you've got this union situation. I mean, maybe I just need to look at the.
You know, I think what you should do is look at this, think about it, and then I'll go with you through it on an exam. Maybe it's good for everybody to see an example maybe on this one. Should we do that and then quit today, do one more example? Here, let me tell you where we're headed with this before I just quit right off the bat. The next thing we need to do is I need to show you how any context-free grammar can get converted to one of these machines. Any context-free grammar can get converted to a non-deterministic machine. And I'll show you that next time. The other direction, that any machine can get converted to a grammar that's uglier and longer and harder, and I'm going to skip it. And I'll just leave it for reference in the book if you want to look at it. But it's true, and that thing's equivalent. I will do the one-way direction, and we'll need Chomsky normal form for going from grammars to machines. And it's not too long. That's about a half an hour of a lecture or so. But too much to do today after this detail. That comes next, and then pumping lemma after that, and then some issues about closure and decision algorithms about these things. So we got about 2 or 3 more lectures on this topic. Yeah, question?
Back to the pumping lemma?
A different pumping lemma, a new one. A new one. It's better. It pumps twice. It's got biceps instead of just one big muscle in the middle. Yeah.
A quick question about this. If you're comparing the first symbol or the last symbol, does that mean you only have one transition of push and pop?
If you can, oh yes, like yes. If you want to.
So like the first part of the first string would then be like right on the middle, so it would only transition.
Yeah.
One.
So Donna's got a good question. She's saying, what if these two symbols? What if these two symbols are at the beginning end of the string, where they could be, right? I mean, it's completely possible that. Oh no, they can't be.
No, both like beginning and middle.
Like here. What if they're? You mean if they're here and here?
Yes.
Well, Donna wants to know, what if the only two symbols that mismatch are the first symbol and the beginning of the middle?
Or the last symbol before the middle and the last one.
Or that. In this situation, you don't push any symbols at all. And you don't pop any symbols at all. The whole thing is the Y section. This is all the Y, and this
pushing
is...
and popping symbols, just not X's. You said you're pushing no symbols at all and popping.
You don't push any symbols for this first section.
Oh, for the first section.
For the first section, you don't push any symbols. Because you have a non-deterministic choice here every single time, whether you're going to push a symbol or whether you're going to read it.
Okay.
If you choose to read the first symbol and then move on to the next stage, you don't end up pushing anything at that stage.
Okay.
And the popping ends up popping nothing. And you end up making a lucky guess, and you just check that this half equals that half. And vice versa, if you do it the other way, then you push everything in the first stage, and there's no Y's to push.
So if it's the first symbol, but you're still going to start pushing first. Because you have to. There's nothing there.
No, you don't.
You're pushing Y's.
You're pushing Y's, but you're pushing something. He's saying
Right.
you're pushing no symbols.
Right.
and
You know, I say here pushing X's and popping X's and pushing Y's and popping Y's. You actually can use the same symbol. It's just that you're likely going to push and pop different numbers of these symbols. That's why I use the different... I didn't mean different symbols you're pushing. You could use different symbols, but you don't need to. You just are going to push the same symbol different a number of times. You get it. All right. I think it might be worthwhile to do this for a second. Erase my pretty color picture and do an actual computation of this machine on a non-even length palindrome, just to show how the computation works. Okay? We do that, and then we'll call it a day.
You mean an odd palindrome?
No.
No.
Well, possibly, but
A
more
non.
likely
Here are two strings. This string really is an even length palindrome.
Okay.
Right? This string is not an even length palindrome. This machine should not be able to accept this. This machine should be able to accept this. So, first let's try to see if we can find a way for this machine to accept this. Not every way is going to work. Let's see, because you know how this machine is supposed to work, whether you can make the right choice without having to guess. So, right at the beginning, you want to go down here or here? If you go up here, you will not accept. That's a bad choice. It's not odd length. So go down here. Now we see a 0. Do you want to push that 0, or do you want to say, I saw a 0 move to this stage? Picking, you say, I saw a 0 move to this stage, means you're hoping that these two mismatch. They don't mismatch. So you better not go there. I'm going to use some color here, if I can. Use red. We haven't used red today. I'm going to write in red what we actually do. We go here. We go here. Now I've seen this 0 and I stored it on the stack. The stack now has an X in it. Now we see this 1. What do you want to do? Don't go through again, because that 1 is the mismatch, and it's the only mismatch. If you don't go down now, you're dead. You'll never make it to the final state. And now we see a 0. What should I do?
No, push.
Just ignore it. Read through it. And now I see another 0. What should I do? Ignore it. And now I see this 0. That's the one I want to mismatch. And now I'm hoping to God that I got exactly one thing left in my stack. I see it. I pop it. It's gone. And now I got no more symbols left. So I can go over here. There's no other computation that would have gotten to a final state here. There are other strings that there were more than one that can get to the end. If there are more than one mismatch, there's lots of ways to get there. But there only has to be one to accept the string. And in this string, there are no ways. Try anything you want from here. Make any guesses you want. Try any of the errors that are legitimately there. You will never get this string to make this machine end you up in here. And therefore, we reject this string. Okay, and that's worth experimenting with a little yourself.